Swayam Prabha. Digital India. Educated India.
Hello, welcome to Introduction to Composites. Today is the 10th week of this course and the first day of this particular week. Over last week, we had been discussing the Hooke's law for anisotropic materials, and we had discussed and we had shown using concept of tensors that in general an anisotropic solid would have 21 engineering constants, stiffness constants, and if we are able to make the structure simpler, then for a especially orthotropic lamina, a unidirectional lamina, this number of constants comes down to 5. And then finally, we had also shown that if the solid, if the material is having special orthotropy and also if the state of stress is plane, then the number of constant it comes down to 4, and for isotropic materials the number of independent elastic constant it comes down to exactly 2. So, that is where we left in the last class, and then we had also developed concepts like the Q matrix, the S matrix, which is the compliance matrix, and what we will do today and in the remaining portion of this week are 3 specific things. One, we will develop these relationships between Q, S and engineering constants for unidirectional lamina under plane stress. This is number 1. The second thing is that we will also find out how do stresses and strains relate if a unidirectional lamina under plane stress is loaded in such a way that the material axis and the loading axis are not necessarily aligned. So, that is the second thing we will do, and then the third thing we will try to accomplish over this week is we will have a detailed discussion of failure of unidirectional lamina under plane stress, and we will also describe several failure theories which are relevant to composite materials. So, that is pretty much the agenda for this entire week, and what we will do today is we will start by having a very quick recap of what we discussed in the last week, and then we will extend that discussion further. So, what we had shown was that if there is a unidirectional lamina under plane stress, then the stresses sigma 1, sigma 2 and tau 1 2, they are related to the strains in the system through a Q matrix, a stiffness matrix. So, the stiffness matrix is something like this: Q11, Q12, 0, Q12, Q22, 0, Q66, 0, 0, and on the strain side we have epsilon 1, epsilon 2 and gamma 1 2. So, these are 4 independent elastic constants, and it should be noted that when there is a especially orthotropic lamina under plane stress, a thin orthotropic lamina, then if I have a shear stress or if I have a shear strain, it will not generate any extensional stresses, and if I have extensional stresses, they are not coupled to shear stresses. So, extensional strains are not coupled to shear stress, and shear strain is not coupled to extensional stress, because these terms are 0. So, this term and this term ensure, in fact these two terms ensure that there is no coupling between the extensional stress and the shear strain, and these terms which are underlined in green, since these are 0, they ensure that there is no coupling between the shear stress and the extensional strains. So, that is there. We had also shown the relationship between Q11, Q12, Q22 and Q66 and the elements of the C matrix which was defined earlier in the following way. So, the system which is under 3D stress state, the relation is something like this: sigma 11, sigma 22, sigma 33, tau 23, tau 31, tau 32, 21. So, this is my stress vector, and this is coupled to the strain vector through a 6 by 6 square matrix, stiffness matrix. So, the strain terms are epsilon 11, epsilon 2, epsilon 3, 33, 22, epsilon, excuse me. So, this is gamma 23, gamma 31 and gamma 12, and the terms in the C are C11, C12, C13, and then the other terms are 0, C12, C22, C23, 0, 0, 0, C13, C23, C33, 0, 0, 0, and then here we have C11 minus C12 divided by 2, then 0, 0, 0, 0, 0, and then we have the same term here, and then we have C66. So, that is how this matrix is constructed. Okay. So, just to clarify, this is 0, and the fifth term in the fifth row, which is the diagonal term, is again C11 minus C12 divided by 2. And just to be consistent, I am going to make this a little clearer. So, because these equations are not tensor equations, these are simple matrix equations. So, I will just call it sigma 1, sigma 2, sigma 3, and this is epsilon 1, epsilon 2, epsilon 3. So, this is the situation. These 6 equations are applicable for especially orthotropic material, which is along two planes of symmetry. And if this material is also in a state of plane stress, then this set of equations, this converges to the first set of equations, because these terms sigma 33 is 0 in a plane stress situation, tau 31 is 0 and tau 32 is 0. So, these are 0 in plane stress, and because it is 0 in plane stress, we can also say that gamma 31 and gamma 23, these guys are 0, okay, and also C33 is 0. So, when you do all this, then you end up with 4 engineering constants, 4 stiffness constants, which are Q11, Q12, Q22 and Q66. So, if we do all this math, then we can show, and we had shown earlier, is that Q11 equals C11 minus C13 square by C33. So, actually I made a small, so this is not 0, but epsilon 3 is 0. So, this is Q1, okay, and then Q22 equals C22 minus C23 by C33, the numerator square, and Q12 is equal to C12 minus C13 times C23 divided by C33, and Q66 is equal to C66. So, these are the relations between the Q's and the C's, and what we see that for a plane stress what really matters are these 4 terms, and they are, so basically we have 4 fundamental elastic constants. So, the next thing we look at is the compliance matrix. So, the stiffness matrix was designated as Q, compliance matrix is designated as S. So, this is a little strange because S one would think would stand for stiffness, but it is for Q. So, compliance matrix is designated by S, and what is the relation between stress and strain if we use the compliance matrix? So, we know that sigma, if I use the sigma vector, if I use the 1-2 plane, this is equal to Q matrix times the strain vector. Okay. This is if material axes are aligned to loading axis. So, this is, and there is plane stress. Okay. So, if material axes are aligned to loading axis and if there is plane stress, then this is the relation which is there, and this we have defined what is the nature of Q's here, we have shown this. Okay. So, now if I multiply both sides by inverse of Q, then what I get is so what I have done is I have multiplied both sides by inverse of Q, and Q inverse times Q is an identity matrix, unity matrix. So, this is a unity matrix, and if I multiply this by epsilon 1 2, I just end up with epsilon 1 2. So, I get the strain, I can express it as Q inverse times Q times sigma 1 2. Okay. So, this the product of these two I call it S, which is the compliance matrix times sigma 1 2. Okay. So, if I know the stresses in a unidirectional lamina which is extremely thin, and if it is in a plane stress trace, if I know the stresses, then if I multiply the stiffness matrix with the stress vector, then I can compute the strains in all the 3 directions. So, what we will do is we will spell out the relations between the S matrix and the Q matrix. So, basically it is just Q inverse times Q, and if I do all that mathematics, what we find is that Q11 is equal to S22 divided by S11 S22 minus S12 square, and then Q22 equals S11 divided by S11 S22 minus S12 square, and Q12 equals S12 divided by S11 S22 minus S12 square. So this should not be there, right. So I will just, yeah, so there is an error. So epsilon 12 is equal to Q inverse times sigma 12. And finally, we can say that Q66 is equal to 1 over S66. So these are the relationships between Q and the S matrices. Q is the stiffness matrix and S is the compliance matrix. Lastly, what we will do is we will look at the relations between engineering constants and Q and S. So suppose I have a unidirectional specimen and the fibers are in this direction, and I just apply sigma L to it. If I just apply sigma L to it, then what will happen? It will also, so it will have, so in this case it will generate what? It will generate epsilon L, and that epsilon L will be equal to sigma L divided by EL. Okay. So if I measure the strain in this material using some strain gauge, and if I measure the stress and if I divide stress by strain, I can calculate EL. Okay. Also there will be a transverse strain because of Poisson's effect. So this is epsilon T, and that will be only because of Poisson's effect. So it will be minus of Poisson TL times epsilon L. It will be LT. Okay. So you can calculate in this way the Poisson's ratio and also the EL. Similarly, if you test this specimen in the transverse direction, you can calculate its ET and nu TL and so on and so forth. And then if you test the specimen by applying only a pure shear load, then you can calculate its GLT. So the point is, by making some simple engineering experiments, we can experimentally find out EL, ET, nu LT, nu TL and GLT, and these two constants are related. Both of them are not independent of each other, because we have shown that nu LT divided by EL equals nu TL divided by ET. So ultimately there are only 4 independent constants. So the question we are trying to figure out is, what is the relationship between 4 independent constants in the Q matrix and these 4 engineering constants, and what is the relationship between 4 independent engineering constants in the S matrix, which is the compliance matrix, and these 4 engineering constants. So the basic thought process we have already explained. So what I will do is I will just directly state the results. So I will say that S11 equals 1 over EL, S22 equals 1 over ET, and S12 equals minus nu LT over EL, or you can also state it as minus nu TL over ET. And finally, S66 is equal to 1 over GLT. So this is how, if you know the engineering constants, we can very quickly find out the elements of the compliance matrix, which is the S matrix, using these relations. Similarly, if you know the engendering constants, then you can also directly calculate the members of Q matrix, and this is Q11 equals EL divided by 1 minus nu LT nu TL. Q22 equals ET divided by nu LT nu TL, and Q12 equals nu LT ET divided by 1 minus nu LT nu TL, and you can also write it as nu TL ET divided by 1 minus nu LT nu TL. And finally, Q66 equals GLT. So we have 3 sets of equations. The first set of equations, they relate Q's to S's, right. The second set of equations, they relate S to EL, engendering constants, and the third set of equations, they relate members of the stiffness matrix Q matrix to the engendering constants. So, we have all sorts of relationships. So, if we have knowledge of even one set of constants, then from that we can calculate all other constants by using these simple relations. So, this concludes our discussion for today. What we will do in the next class is we will have a very brief continuation of the same discussion, and then we will move on to transformation of these engendering constants if the loading direction is not aligned to the material axis of the system. So, with that conclusive remark, I close our discussion for today, and I am sure that you will have a wonderful evening, and I look forward to seeing you tomorrow. Thank you.